Hello everyone, I'm Christian Pinto from IBM Research Europe, and in this video I'll talk about our paper on ThymesisFlow, an open source framework enabling rack-scale software-defined memory disaggregation. But what is software-defined memory disaggregation? In a classic data center, we have compute nodes equipped with memory, CPU, connected to each other via network, either Ethernet or InfiniBand, for instance. Applications run on the compute nodes in a either bare metal or virtualized fashion, having the same limitation that they can only consume as much resources as they are available on each single node. If an application needs more resources than what is available on one node, you need to scale the application out. So replicate the application and have the replicas interacting via network. In a software disaggregated setup, the application is running on a so-called software-defined compute node. So the hardware nodes are connected to each other via a dedicated disaggregation fabric, and the orchestrator can compose resources across multiple nodes. So as you see here in the example, the application needs more memory available on one single node, but instead of scaling out on the two nodes, we use the resources for one node plus get some memory from another node via the disaggregation network. The CPU on the other node remains free for being used by another application. Why are we doing this? It's because by doing resources pooling, we can remove some of the main limitations in today's data center, in the design of today's data center, which is by defining the proportionality between resources at the same time, meaning the node, you incur into having low utilization and jailed resources. Jailed resources are those resources that are free, but they cannot be used. For instance, you have free memory, but not enough CPU cores for using this memory. So this memory is actually wasted. This leads to a high cost of ownership and, of course, in a low energy efficiency. Also, the design based on the single server trade is also giving you a locked refresh cycle of peripherals. We have done a simulation of the Google cluster data using a custom simulator that models a disaggregated and a standard data center and uses a best fit scheduler to place arriving VMs to nodes. And with this simulation, we have seen that there are tremendous opportunities for reducing the fragmentation of resources, meaning the jailed resources, and also huge opportunities for powering of resources that are not utilized. So at IBM Research Europe, we started with disaggregating the memory, and we have built ThymesisFlow, that is an open source framework enabling hardware-based memory disaggregation. It uses OpenCAPI coherent attachment and targets a Power 9 processor. We have 100 gigabit per second internode disaggregation fabric and a full software stack that enables out-of-band configuration of the disaggregation system and full integration with the Linux memory subsystem so that disaggregated memory appears as completely transparent to applications. Here you see the full stack prototype of ThymesisFlow. And from now on, you always have to consider that in ThymesisFlow and in disaggregation, there is always a node called the compute node, that is a node borrowing the memory, and the memory node, that is a node actually lending the memory to a remote machine. Let's start having a look at the hardware design. The first thing to be discussed is that we rely on OpenCAPI coherent attachment, and in the specific, we use the OpenCAPI C1 mode for the memory node that allows a peripheral mastering cache coherent memory transactions, and the M1 node on the compute node that enables a peripheral to show up as a memory-like device on the bus. Each OpenCAPI peripheral is attached to the CPU with the 200 gigabit per second serial link. Our custom design is composed of three main parts. On the compute node side, the main activities are interfacing with OpenCAPI, of course, and then performing mapping of physical address space location with remote memory locations, and also converting addresses from the compute node physical address space into the remote memory node virtual address space. These tasks are performed by the remote memory management unit, or RMMU. The compute endpoint is also steering traffic towards the remote destinations. On the memory endpoint side, instead, we again have the interfacing with OpenCAPI. And the main task is emitting OpenCAPI transactions towards the local memory of the Power 9. This is because the way ThymesisFlow works is that the CPU on the compute node emits a memory operation. This is translated into an OpenCAPI transaction that flows through the ThymesisFlow network and is emitted at the remote memory destination. Of course, responses are sent back if needed. The interfacing between compute and memory endpoints is done via a network, and we have a custom link layer control that implements back pressure based on credits, and we have a reliable channel thanks to retransmission based on CRC check. And the network bandwidth is 100 gigabit per second for each network link. So our prototype uses an FPGA with 2 physical links. This means that we could bond the 2 channels and benefit from 200 gigabits per second. On the software side, instead, we have on the compute endpoint software for configuring the RMMU, so mostly configuring the address translation and hot plugging the disaggregated memory to the running Linux. On the memory endpoint side, instead, we have a process that is reserving the memory for remote access, because disaggregation is not happening by stealing the physical memory, but it is actually a process at the memory node that is allocating the memory for remote access. Finally, we have an orchestration software that is overarching the full prototype, and it's used for dynamic attachment and detachment of disaggregated memory from compute nodes. We have evaluated ThymesisFlow with a set of applications. The first is Stream, that we have used for measuring the raw bandwidth. The other are 3 classes of cloud applications, like in-memory databases, in-memory application level caching, and data analytics. The idea is that all these applications can be replicated on multiple nodes, because, for instance, you need for memory to host more data. So the benefit of using ThymesisFlow for the 3 applications is mostly that you can get more memory by just using half of the cores, CPU cores. And only for one, which is memcached, using ThymesisFlow has an additional benefit, because when you scale up memcached to multiple nodes, you have to usually use a proxy between the clients performing the requests and the memcached servers. When we use ThymesisFlow, since everything keeps running on one CPU, you don't need to have a proxy in between. So you are further reducing the network latency and the network hops between clients and the memcached servers. Our hardware setup is composed of 2 AC922 power servers that are dual socket Power 9 machines. The ThymesisFlow custom design is implemented on the Alpha Data 9v3 accelerators that are OpenCAPI enabled FPGAs. And the network fabric is a point-to-point connection with 100 gigabits per second on each link. The 2 FPGAs have 2 ports, so there are 2 links between the 2 machines. We compare 4 configurations: local memory, application uses only local memory; single bonding disaggregated, which means applications only use disaggregated memory, but we either use 1 or 2 links between the 2 machines, so 100 or 200 gigabits per second ThymesisFlow. The interleaved, which is applications use a combination of local and remote memory in a 50-50 fashion. And finally, the scale out, which is the main one we want to compare against, which is I need more resources for my application. What I do is I scale it out on 2 nodes so that I can benefit from double the resources. First benchmark is Stream. So we have run Stream using 160 million array elements, so that they are bigger than all the caches available on the system. And we compare all the 5 configurations, and here we show gigabytes per second for 4, 8, and 16 threads for all the kernels. So the main things to be noted is that in the single disaggregated case, for 8 threads, we reach the maximum ThymesisFlow bandwidth. So we can reach the maximum bandwidth of 100 gigabits per second on one link. And we notice also that going beyond 8 threads, the bandwidth reduces. This is because we are saturating the network pipelines in our design that were already working at the maximum speed. Interesting to see is that bonding is providing around 30% higher bandwidth, not twice the bandwidth as one would expect. This is because of the type of open copy transactions that we use, which is 128 byte transactions. We should switch to 256 bytes transactions to fully exploit the link between the off-chip peripheral and the Power 9 bus. But this is not possible because the CPU only emits 128 bytes transactions. Finally, as expected, interleaving is greatly improving the bandwidth because it is mitigating the remote memory access penalty. The first example that we see here is VoltDB in-memory database for two classes of benchmark. The benchmark is the benchmark clients are using YCSB, the Yahoo Cloud Serving benchmark, and here we see the throughput in operations per second for 4 and 32 partitions. The number of partitions is representing the parallelism of the application itself. So we see that for disaggregated memory, a higher parallelism is actually beneficial because having more threads means that while some threads are waiting for memory to come back from disaggregated memory, other threads can take over the CPU and do some meaningful work. Also, we see that for 32 partitions, the scale-out and single-bonded disaggregated show the similar performance. This means that with disaggregation, we can have the same throughput of a scale-out scenario, but using half of the CPU cores, which is quite a good result for us. And overall, we have measured a 10% reduction of throughput with respect to the local memory scenario. The second application we have evaluated is Memcached. So for Memcached, we use the Facebook data center traces. Here we show the CDF of the get transactions latency for all the 5 configurations. We see that overall, in average, transactions are served with a 7% increased latency when using disaggregated memory, either single or bonding. And surprisingly, the scale-out is also slightly slower than disaggregated memory, and it also has a quite higher latency variability, because we have seen that for 90% of the requests, the latency is twice as what is the average latency. This is because in scale-out, we have a proxy between the clients, the application clients, and the servers. While with the disaggregation, we can remove remove the proxy and thus remove one network hop that can increase the variability of the transaction itself. The last benchmark that we have evaluated is Elasticsearch. So for Elasticsearch, we used their default benchmark suite, which is called ES Rally. And here we show throughput in operations per second for all the challenges and a comparison between 5 and 32 shards. Shards, again, gets translated in the more shards, the higher is the parallelism. So the main takeaway from that we got here is that scale out for Elasticsearch is always giving us a higher throughput, in average 45% higher than both scale out and both single or bonding disaggregated. This is mostly because of the nature of Elasticsearch, that differently from SQL-like databases, here having more cores, more threads, means that I can run more, can crunch more data and thus have a higher throughput. More interesting again is that for some challenges, the scale out is even faster than local. So this is further strengthening our hypothesis that Elasticsearch is highly benefiting from having more cores available rather than just having more memory. So in general, we have seen that For Elasticsearch, memory disaggregation is not as beneficial, but it could still be an appealing approach in case someone wants to trade performance for cost, so lower number of CPUs. So in this video, I've talked about ThymesisFlow. It is one first of its kind open source framework for compute peripheral disaggregation. ThymesisFlow enables fully transparent attachment of remote memory, and for some classes of application, it's actually an appealing alternative to scaling out on multiple nodes. In the future, we will be working on better integrating with the Linux NUMA policies for latency reduction, run bigger scale experiments, and exploring the network fabric, like having packet versus switched network, and also should we keep on the single rack or should we consider disaggregation at the multi-rack level. Thanks very much, and if you have any questions, please join the Q&A session. Thanks.